My name is Luke Polson. I'm a PhD student at BC Cancer working on the Pi Tomography open source reconstruction library for medical image reconstruction. And today I'm going to show you how to use the SlicerSPECTRecon SPECT reconstruction extension. This extension is a graphical user interface that you can see here. It's an extension for 3D Slicer, which is a 3D image viewer typically used for medical imaging. And our extension allows you to take in raw SPECT data or projection data, use various algorithms to reconstruct it, and create 3D SPECT images. This video is a tutorial demonstrating how to use the extension, and so there's a few things we'll need. This is the GitHub page for the extension. This is where we'll download it from at the moment. I'll put a link in the video to this page as well. And so eventually, SlicerSPECTRecon will be an official 3D Slicer extension. In that case, you can come to the app, click on the extension module thing here, go to install extensions, and you could look up SlicerSPECTRecon. Unfortunately, you won't see anything now, but in the future, and we'll make a note in the description of this video as well, you may be able to install here. But at present moment, when I'm recording this video, it is not an official extension. And so what you need to do is you need to download it from GitHub. And so that's contained in the user manual, how to do that. You can either download it directly as a zip file, or you can clone it on GitHub to a location on your computer. And then either way, you can basically add it as an extension. And that's basically summarized pretty well in the installation part of this tutorial. So in this tutorial, I will assume that you've already got this set up and you're ready to start using the extension. The other thing that you'll need is the tutorial data. I have a link here in the user manual of where to get it. You can basically just follow this link. There'll also be a link in the description of this video, and you can see the SPECT data that we will be using to reconstruct. Okay, so here I have 3D Slicer open. I'm just going to drag this up top. And in order to use this extension, you need to know a little bit about 3D Slicer and sort of how it interfaces with the extension as well. And so the idea is that with this extension, all the data, all the DICOM data or the raw SPECT data that you're going to load in comes as DICOM format. So you would load it as you would typically load in DICOM data in 3D Slicer. So I'm just going to delete these for now because you won't have them. You know, kind of probably if you're just using 3D Slicer for the first time, you'll have this blank page here. And what you want to do is you want to go import DICOM files, and you want to go to the location where you downloaded the tutorial data, which I have right here. And for now, we'll just choose the DICOM folder. We can click on this and we can click import. And what it's going to do is it's going to import these three things. So these are two bed positions from the SPECT scan of the patient. So they took a SPECT scan in the upper field of view, SPECT scan lower near the pelvis. And you could basically combine these together to get a full field of view SPECT image, as well as a CT image. So those of you that know SPECT reconstruction well, you know that in order to get a quantitative SPECT image, you need to account for the fact that some photons, when they leave the patient, get attenuated in the patient. So you need what's called an attenuation map in order to account for that in your reconstruction algorithm. And the way that you obtain those attenuation maps, typically in SPECT, is through CT images. So whenever you take a SPECT scan, there's typically a CT scan that you take as well. So in this case, we have all the data we need to get a full body SPECT scan. And so what we can do is we can basically hold control and click on all three of these, and then we can load, and we should load all the data into 3D Slicer. So again, I'm going to drag this up, and what it's showing right now is the projection data. It's actually showing a sinogram here, but what we'll be interested in is the actual sort of rotating projection. So you can actually see as I scroll through this, it's doing full rotations and it's getting darker and brighter. The darkness and brightness is the different energy windows of the photons they acquire. So for example, photons here are between certain energy values, and photons here are obviously different energy values. And with the radioisotopes that they use, you get higher emissions at certain energies. And in this case, they've collected 6 energy windows, and this corresponds to lutetium. Now we can look at, this is the lower field of view, but we can also look at the upper field of view as well. It's right here, and what I'll do is, by the way, if things get off-centered like this in 3D Slicer, you can right-click, and you can go reset field of view, and it'll put it right in the center. So this was the upper field of view of the SPECT projections as well. So you can see sort of the face and some of the bones here in the patient and the upper part of the liver. So this is the SPECT projection data that we are going to reconstruct. And then of course there's also the CT data as well. So again, usually when you're dealing with SPECT raw data and CT, things get misaligned in 3D Slicer. So I'm going to click Reset Field of View, and this is the CT scan that we'll be using for reconstruction. Okay, so up until now, we've basically just loaded in the data that we've required for reconstruction, but we haven't actually used the extension yet. So what I'm going to do now is I'm going to go to the tomographic reconstruction thing here, and then we have SlicerSPECTRecon. So this is basically the UI for reconstruction, and those of you that know about SPECT reconstruction, you know basically the idea is to take in the raw projection data, create a reconstruction algorithm that then spits out a three-dimensional image. So you can see our projection data here, obviously. So I'm just going to do a really quick reconstruction first. So what I'll do is I have my projection data tab here. You can see that I have both bed positions, and I can select one or I can select both. So if I select both, what's going to happen is it's going to reconstruct both and then stitch them together to get the full length image. And just be careful not to select the CT here. Once I select those, then I can select the photopeak that I want to reconstruct. So this data corresponds to lutetium. So those of you that, again, know SPECT imaging, you know the main photopeak of lutetium is 208 keV. And then there's also some scatter windows as well. And then there's another photopeak you can reconstruct. For now, we're just going to choose this photopeak. We're not going to worry about any of the system modeling stuff for now, but basically we'll just go down to the reconstruction algorithms and we'll say, okay, let's reconstruct with OSEM, ordered subset, expectation maximum. And just to show you how it works, we'll go 5 iterations, 1 subset, and I can click reconstruct. What's going to happen is a loading bar is going to come up here. It's going to reconstruct the data. And once the data is reconstructed, it will be displayed in the window here. So here you can see the axial, coronal, and sagittal reconstructed images, and obviously I can scroll through them and move through the various slices in 3D Slicer. What I'm doing here is I'm holding Shift and just moving the mouse, and you can see all the stuff. But obviously this is not a good quality image. We haven't used attenuation correction, we haven't used PSF correction, we haven't used scatter correction. And those 3 components, again, those of you that know SPECT reconstruction, know that those are very important to get a good quality quantitative SPECT image. So the first thing, by the way, we should do is we should go to data and we can name this. So what I'm going to do is I'm going to name this OSEM. I'm just going to call it no physics because we didn't do any modeling, and we'll call it 5 iterations, 1 subset. So that was in the data module. So now I know the name of this and it's sort of displayed down below. We can go back to our extension, and I'm going to keep both bed positions selected. And I'm going to start introducing some things in the system modeling. So of course, the first thing we can do is attenuation correction. So this actually uses the CT image that we've loaded. By the way, you can actually view both of these things together. I can select the CT image. So what I did is I clicked here. I'm going to click the CT image. We'll display it. And what I can do is I can actually put the reconstructed SPECT image on top. And you can see they align with each other. So in SPECT reconstruction, you can use the CT image to adjust for the fact that the photons get attenuated as they leave the patient's body. So we can click attenuation correction. We'll set the attenuation map that we've loaded, and that compensates for that. The next thing we can do is we can do collimator detector response modeling, or PSF modeling. We have to select the collimator code. So these are all on the PyTomography website. You can actually see this table here. There's a link that I'll put in the description as well. You can see all the different collimator codes for the various SPECT systems and collimator types. So what you can do here is we can select. So here we use the GE medium energy general purpose collimator. Here you can put the intrinsic resolution of the crystal, which is usually put at about 0.36 centimeters. And that sort of takes care of collimator detector response modeling. The next thing we can do is we can select scatter correction. So the current way that we implement this in SlicerSPECTRecon is energy window-based scatter correction, though in future releases of PyTomography, there will also be Monte Carlo scatter correction. But for now, we just have the energy window, so we can select the upper window and the lower window. So we have this main window between 187 to 228, and we can select these windows to do triple energy window scatter correction. So that adjusts for the fact that some of the photons, as they're leaving the patient, they don't travel straight towards the detector, but they actually travel, interact with the patient, scatter, and then get detected in the detector. So we can set scatter correction. There's likelihoods as well. So again, for now in the extension, the default is the Poisson log likelihood. This likelihood, it perfectly characterizes the SPECT data. It says that each detected event in each bin on the detector is a Poisson random variable. but maybe in the future we'll have some other options so that people can test other likelihoods as well. So now we have like basically a full system model for the SPECT system. Again, we'll use OSCM, and now we'll do the typical reconstruction that's used in the clinic. We'll go 4 iterations, 8 subsets. So everything we've specified here corresponds to a pretty traditional SPECT reconstruction that you would see on an actual patient image. So we can click reconstruct. And once again, we should get a loading bar that comes up. And here it is. And it's just slowly reconstructing. And now we should get our final reconstruction that will be displayed in the windows here. So here's our full reconstruction, 4 iterations, 8 subsets with the modeling that we put. And again, we can do the same thing where we put the CT image below, and then we can put this new reconstructed image above. So this is sort of what you would call a typical SPECT image that you would get doing all the typical system modeling. So let's go back to data, and we're going to rename this OSCM all physics, 4 iterations, 8 subsets. So this is a very typical SPECT reconstruction. So the image reconstruction extension, of course, offers other capabilities besides just generic clinical recon. So we have other algorithms as well. We have BSREM, and we also have OSMAP, OSL. So this is block sequential regularized expectation maximum. And this is a sort of another Bayesian reconstruction algorithm. So I can select BSREM. When you reconstruct with BSREM, you typically use more iterations. So I'll use 20 and 8. What BSREM allows you to do is it allows you to specify a prior. So here I can select a prior function to use. For this example, I'm going to use the relative difference penalty. And then we can actually select the parameters we want. So usually in research, when people are doing BSREM with SPECT, and I think GE offers it as a clinical product, they would use about 0.3 for this parameter beta and 2 for gamma. In fact, they don't typically expose gamma to the users, but this is another hyperparameter for the prior function that we can actually adjust as well. And before I use anatomical information, I'm just going to reconstruct this. And I just made a mistake. I didn't specify the CT map when I just reconstructed. I just changed that now. So I just clicked reconstruct again, and I made sure to specify the CT map, and it gave me an error that I saw in the Python console. So it's creating the system matrix. That you don't actually see a loading bar during that process, but now you can see the reconstruction loading bar. So it takes about 10 to 20 seconds to build a system matrix. Now we can actually see the reconstruction. Okay, so now that it's reconstructed, I'm going to go to data, and I'm going to call this BSREM with the relative difference penalty, and I'm going to name it 20 iterations, 8 subsets. And what we can do is we can actually now compare some reconstructions. So I can look at BSREM, for example, on this tab. And then here, for example, well, let's bring up actually, let's put them in order. So here we'll do OSCM 4 iterations, 8 subsets. Here we'll do the no physics one, and we'll make sure it's a coronal slice. And then here we'll put the BSREM one in coronal slice. So you can actually see the 3 different reconstructions. So this is no physics modeling. You can see that the image quality is pretty bad, and you can see a lot of scatter and counts that have been assigned outside the patient. Of course, I can scroll through it because it's a 3-dimensional image. Here's the reconstruction with the PSF modeling. This is the standard kind of clinical reconstruction that you could expect to get. And then here you have the BSREM, which is a prior reconstruction algorithm that keeps the counts a little bit smoother. So this is reconstruction using that, which is somewhat of a newer reconstruction algorithm. So there's a couple more features as well. So here I'm going to select the CT again as well and make sure that everything is selected before I reconstruct. We also can use anatomical information when reconstructing with a Bayesian reconstruction algorithm. So here what I can do is I can actually use the CT image that I've loaded, and I can use the 12 nearest neighbors to see the area where I'm smoothing the prior. So typically with something like BSREM, you want nearby voxels to be similar to each other. So it creates a smoothing sort of effect. Here I can say I want nearby voxels to be similar to each other, but only the 12 most similar voxels based on the CT. So now I can sort of account for edges across organs and things like that. So I can reconstruct this as well. Okay, so our reconstruction is almost finished here. You can see by the loading bar. And we should now get a new BSREM image displayed. Of course, this is a anatomically reconstructed image. So you can actually see if I go to the bones here, you can see how it's kind of confining some of the activity to some of the spine vertebrae here. And you can see, especially in the bone, how the activity kind of matches that. So that's one of the features of these sort of anatomically guided reconstruction algorithms. You can especially see it here in the spine. So there's a few more things that this extension has to offer. So I'm going to actually go back to OSEM, and we'll just set this back to 4 iterations, 8 subsets. So we can go back to the system modeling. What PyTomography and the SlicerSPECTRecon graphical user interface allow you to do is you can also do multi-photopeak reconstruction. So with this, I can select my projection data as the 2 bed positions here. And I can actually specify that I want 2 photopeaks, and I'm going to specify the 208 keV peak, and I'm also going to specify the 113 keV peak. Now, when you're doing reconstruction like this, you have to scale each one by its relative calibration factor. So typically for something like 208, I think these are rough numbers. You get something around 10.3 and 11.3 for various scanners. It's slightly more sensitive in the 113 peak region. In this case, now I'll select the CT again. When you're doing scatter correction, you actually have to specify the upper and lower windows for both peaks. So here I'll select the upper window corresponding to photo peak 1, which is the 208, as well as the lower window here. So here's the upper window and the lower window as well. So now I can use this system model. Now it's going to incorporate counts from both energy windows when it does the reconstruction. So here I have OSEM, 4 iterations, 8 subsets, and I can reconstruct. So you can see it reconstructing here. Sometimes it takes a little bit longer till it gets to this reconstruction point. Now you can see the loading bar, and now it will give me a dual peak reconstruction of lutetium 177. It'll take a second to load, and then we'll see it in the display window. So here's the dual peak reconstruction that takes into account counts from both the 208 peak as well as the 113 peak as well. So I'm going to go back to single peak reconstruction. We're just going to do the 208 keV peak. And the final thing that this extension has to offer at the moment, and I'm going to specify CT again, is we can actually do uncertainty estimation. So there's a recent paper that our group published that you can see here that we just submitted to IEEE. And it's all about predicting from a region of interest, what is the uncertainty. So for example, if I'm looking at the kidney here, and I scan the same patient multiple times, I'm going to get a slightly different SPECT scan each time, and I'm going to get a slightly different uptake in the kidney each time, even though the patient is exactly the same. And that's due to the random nature of the emissions of radioactivity. And so you can actually ask, well, how much is that going to vary scan to scan? What percent difference, for example, is the total uptake in the kidney going to be? And this is where 3D Slicer really comes in handy, because 3D Slicer, as you know, and I'm just going to show the CT image here, 3D Slicer has Total Segmentator as an extension where you can segment every organ on the CT image. So I can go to segmentation. I have this installed. By the way, if you don't have this installed, you can go to the extensions. You can go install extensions, and you can look for Total Segmentator. So this will actually segment all the organs from a CT image for you. So what I can do is I take my CT image here, and I'm actually going to go to segmentation, not segment editor. We're going to go to Total Segmentator, and I'm going to choose the CT image, and I'm going to do a fast total segmentation. So here we can see all the segmented organs, and I'm actually going to put the CT image here. We'll put the OSEM reconstruction here, and we'll just do that for now. And you can see basically the segmentation masks at all the different organs based on the CT, and then we can use that to get statistics for our SPECT image as well. So what I'm going to do is I'm going to go back to the SlicerSPECTRecon extension, and we're going to do one final reconstruction. We'll just do a regular OSEM, 4 iterations, 8 subsets. But what I'm going to do is I'm going to click this Store All Iterations. So in order to estimate the uncertainty, one of the things that you have to do in the algorithm that's written is you have to store sort of the update of the 3-dimensional image at each iteration in the iterative algorithm. So I'm going to store all the iterations. This is something you need for uncertainty estimation, and I'm going to click Reconstruct. We're going to go back to data once it displays it. This is our typical OSEM 4 duration 8 subsets. Let's go to data. It's the last one, and we're going to name it just OSEM normal, I'll call it. Then what we can do is we can go back to the extension here. And you'll see at the very end, there's something called post-reconstruction. And then there's options here. We're going to select uncertainty estimation. And what I can do is I can select my reconstructed image, which is OSEM normal. I can select a segmentation. So I'll go to the segmentation, I think is what it's called, or maybe it's this segmentation. And I can choose a various organ from the total segmentator segmentation. So let's, for example, choose right kidney. And from here, I can compute the uncertainty. So I click on compute uncertainty, and it takes about the same amount of time as the reconstruction per organ. So it is a very computationally expensive algorithm in the sense that it requires basically the same computational time for the entire reconstruction as for each volume that you're estimating the uncertainty for. But I can click this, and we'll wait. I think I renamed the wrong image, so I think it's actually this last reconstructed image. Let me go back to data. And yeah, there's actually one that we did after. So this was the wrong one that I named. So this is technically the correct one at the very end. So that's why it gave me the error in the Python console. So we'll go back to the SlicerSPECTRecon extension. And now we're going to choose this last one. So this is the one that we've stored all the iterations for. And now I can click compute uncertainty. Okay, so the computation of uncertainty just finished. You can see that it's built a table here. It has the reconstructed image, the segmentation, the name of the mask, and it has both the absolute uncertainty in counts as well as the percent uncertainty, so it's about 0.87%. What that means is that if I scan the patient the exact same way and the exact same patient multiple times, the total uptake in the kidney is going to vary about 0.87% between different scans. And obviously it depends how long you scan the patient for. So if you put a scan here and reconstructed it where the patient was acquired for a very short amount of time, this uncertainty, this percent uncertainty is going to be quite a bit higher. Now, if I were to go and I were to do this for another organ, say the liver, and I compute the uncertainty, then it automatically gets appended to this table here. And now you can see the mask is liver, and the liver, being a larger organ, has a less of a percent uncertainty in the total activity. So that basically covers the DICOM portion of the tutorial. Now we're going to go into how to convert SIMD data into DICOM format so that we can then reconstruct simulated SIMD data as well. Okay, so I have a fresh slicer thing here. What I'm going to do is I'm going to go to my SlicerSPECTRecon. There's no data in this 3D slicer instance yet. And what I'm going to do now is I'm going to close all of these. And what we're interested in is converting SIMD simulated data into DICOM data. So this is where the data converters tab comes in handy. Right now, the only converter that we have is SIMD to DICOM because I know a lot of people are going to be interested in reconstructing Monte Carlo generated SPECT data as well. So we can click on this, and this gives us the options to convert. So when you simulate data in SIMD, if it's projection data, you would store the different energy windows of your data in different files. So remember with the lutetium example we just had, there were 6 energy windows. Now in this example, and this comes with the data that you downloaded, there's going to be 3 energy windows. So I'm just going to say that there's 3 energy windows. And with SIMD data, you simulate a very, very, very large number of counts, and then you subsample to get the counts that represent a typical SPECT scan. So we've simulated like a ridiculous number, and now we're going to say, okay, for this particular data we want to reconstruct, we're going to say that it's equivalent to 15 seconds per projection with 1,000 megabecquerels. And the reason why this says megabecquerels or megabecquerels per milliliter is because when you set up your SIMD simulation, you can actually choose for the units of the output to be in counts per second per megabecquerel, in which case you multiply by 15 seconds, you multiply by 1,000 megabecquerels, and you get counts. Or the units could be counts per second per megabecquerel per milliliter. And in that case, you would actually have to store by, you'd have to scale by the megabecquerels per milliliter, the activity concentration that you've chosen for that SIMD simulation. But typically you would just choose megabecquerels. And then because we're creating random data, we can choose a random seed. And now we can choose the 3 windows that we want to convert. So here I'm going to go back to where I downloaded the data, which is for SlicerSPECTRecon, SIMD. And I'm just going to select the header files, the H.not files of the 3 SIMD things that I've simulated. So there's W1, W2 header file, and W3 header file. So I have these, and I can name my patient. I'm just going to call it JSAC. That's the name of the phantom. It's a cylindrical phantom with 3 spheres. And what I'm going to do is I choose a location that I want to save it. So I'm actually going to create a new file here, and I'm going to call it SIMD to DICOM. So this data is going to be in the DICOM format. So I've converted my SIMD into DICOM. So I'm going to select this folder. This is where the data is going to be saved, and I'm going to click export. So now it's exported to this file, and we can check that. We can confirm that. So if I go to this file, you can see that we have this folder here, and I now have my DICOM file where I've converted that SIMD data into DICOM format. So the next thing we need to do is we convert the attenuation map that's output from SIMD into a CT file. So what I'll do is I select the file that I want. I'm going to go to SIMD, that's where it's stored, and I'm going to take the attenuation map .hct file. I'm going to open that, and there's an output folder, and here I'm just going to put it in the same folder, the SIMD to DICOM folder, and I'm going to go create DICOM files. And so once I click that button, it's really fast, and you can see that I have both an attenuation map here as well as SPECT projections. So now that the conversion is over, I can close the data converters tab, and we can sort of reconstruct as usual. And the reason why we've converted to DICOM, of course, is because 3D Slicer it can't manage SIMD data, but it can manage DICOM. So what we'll do is we will load this DICOM in the same way we did before. We'll click DICOM. Here we'll go import DICOM files, and I'm just going to click on the whole SIMD to DICOM folder. What it's going to do is load this, and it's the name that I gave it, which is JSAC. And I'll load all this data, and I'm just going to click OK. So here you can see all the projections from the SIMD data, which we have now created with a given time, scaling, and random seed. So we can go back to the SlicerSPECTRecon extension. I can select the projection data, which is this thing here. And the photo peak, it gets loaded as it did before with the DICOM. I'm going to select the 208 peak for lutetium. I'm just going to do a regular reconstruction here. So I'm going to select the CT/attenuation map. Here it was a Siemens medium energy collimator, and we'll say the intrinsic resolution is around 0.36. Scatter, we're going to use energy window. This is the upper window, this is the lower window, and we're just going to do an OSEM with 4 iterations and 8 subsets, and I can reconstruct. So it's just finished reconstructing. It's now just loading it into the window. It should be any second now, and you can see the reconstructed image. Now it doesn't look great, and the reason for that is that the scaling is totally off. So I'm going to go to volumes. I'm going to select the reconstructed image as the active volume. I'm going to go to the window level. I'm going to set manual minimum maximum. I click the ... here. I'm going to set minimum to, let's say, 0 and the maximum to 20. And now I can actually adjust the window level, and you can see that this scan here is representative of a sort of a typical phantom scan that you might do as a SPECT acquisition. And so I have both the axial, coronal, and sagittal views of this phantom, and we've now reconstructed SIMD data using the SlicerSPECTRecon extension. So before I finish, there's a couple limitations that the extension currently has. The main ones are actually this uncertainty estimation thing here. So right now, the uncertainty estimation only works for OSEM, and it works for BSREM with the relative difference penalty. If you try to compute the uncertainty for any other reconstruction algorithm at the moment, it is not going to work. And I should also mention, if you like the reconstructions of this and you're also interested in Python coding, you can also go straight to PyTomography. We have this documentation page. This is a Python library that the extension is built on. And there's tons of tutorials to demonstrate how to reconstruct SPECT, PET, CT data. And I can click here for the tutorials, and you can actually see a lot of the code that's basically the back end of what's going on in the SlicerSPECT recon extension in order to reconstruct these sort of objects. Anyways, thank you for watching and happy reconstructing your images.